Hey guys, this is a teardown of an Ektapro EM high-speed camera system. This consists of this large processor unit and this camera head interconnected by a giant multi-way connector. This records 240 by 192 video at 1000 frames per second. This was made by Kodak. I think this system went on sale around 1990 and sold for something like $70,000. On the back side there's connections. This supports up to 2 imagers. Bunch of video outs, trigger in has GPIB, power in the bottom is probably the power supply in the bottom and all the electronics up top. I did a quick intro video on the system showing how the system operates. Click on the link here to see it. Just trying to figure out how to get this thing apart. It doesn't look like any of these screws around here are going to do it, but I think there might be something hidden under this little panel here. Some incredible effort went into construction. I mean, there's these extruded aluminum pieces just as sort of inserts with printing on them. Yeah, it looks like there's screws under this that will come out. I'm hoping the whole top section will pop off. Yes, that sounds like it. Yeah, that seems to be coming. Looks like just the back end's got to come off, or perhaps the entire bottom will just slide out. Oh, look at all that. Classic 90s stuff. What do we have here? Lots of classic card cage, lots of ribbon cables all over the place, and it looks like SIP module RAM. Wow, look at all that. I think this has something around 200 megabytes. I'll have to count it up and see what it's actually got. On this side we have what's probably power supplies, judging by all the heat sinks. Over here there's these boards that break out the giant circular connectors onto IDC headers for the cables that run up to the top. These are labeled IID, IA. I think that's interface digital, interface analog. Let's start pulling some of these, pulling the cards out of the card cage. Let's fly over the sea of boards. Anyway, there's 15 cards in this. I've labeled all the connectors with numbers so I know which one goes back where. Let's just start pulling these out and looking at them. The first board is labeled the image digitizer module. This board is absolutely packed full of ADCs and digital logic. On the bottom, the analog video comes in from the bottom, 16 analog channels. These lower chips are 8 megahertz fed input op amps. Those probably amplify the signals before going into, or buffer signals before going into the ADCs. These are BT208KP ADCs, 18 megasample per second, 8-bit flash converters. You don't see flash ADCs very much anymore. So the outputs from these go into numerous 74F166 8-bit bidirectional shift registers. And interspersed within those are these MC10124 TTL to MECL buffers. It appears what they're doing is serializing the output from parallel output from ADCs into serial using these shift registers. And some tap goes through these. There's 4 of these TTL to MECL converters. That data goes up. You can see these traces up to these parts, MC10158. Those are 2 input multiplexers, again MECL, and that goes out into this connector, and this goes over to the next board over, which is labeled just EDM. I believe the serialized data from the ADC, from the shift registers, goes up to these parts. These are MC10176. That is a hex flip-flop, and the one above it, you can see those, the data output, these are parallel output devices of some sort, connects up to this large connector here, and this one went over to the RAM controller board. These are MC10192, which is a quad bus driver, differential bus driver. That sort of makes sense because that went over, it looks like they're using all 40 lines on this connector, and that goes over this relatively long cable to the across here to this board, which is labeled the memory controller. So it's likely that obviously, if they're sending parallel data over this, you need to have several ground wires, ideally one every second one, but they're not doing that, so these must be sending differential data over that. This part up here is an ECL delay line producing 30 nanoseconds of delay. And of course, for something like this, made in USA. I just pulled out the second module, and just looking at this, it becomes a bit more clear what's going on the ADC board. This connection connects over to this one here. This has a more TTL to MECL converters. So these signals are coming out of this connector and coming in here. So apparently what this is doing, definitely these chips are serializing the output from the ADCs. The ADCs run at about 3 megahertz, so this will run at something like 20, 25 megahertz or something. The outputs of 4 of the serializers go into one of these quad TTL to MECL converters, and all of the ADC data comes up these lines to these muxes. Those can switch the outputs either all from the ADCs or all from whatever the output of this is. I'm thinking this might be some sort of cursor or text or some generator to burn text data or cursors into the image recorded in RAM. So that's probably what the multiplexers are for, so you can select either image data or overlay data. The outputs from these then go over to these differential drivers, or actually through these registers, then through the differential drivers, then onto the output cable over to the RAM. And for those of you who don't know, ECL is emitter-coupled logic, which is an older form of high-speed logic that has a much lower propagation delay and higher maximum frequency than TTL or CMOS chips. But these parts dissipate a lot more power and require odd negative voltages to operate. On the EDM board, there's not that much. There's the main chip, which is a Xilinx XC3064 FPGA that has about 220 logic elements. There's a bunch of 74 series logic, a few lattice gals, and those TTL to ECL converters. The third board is the dual imager interface analog board. This takes the 16 differential analog differential channels from each camera, so one in each port, converts them to single-ended, and multiplexes them and sends them to the ADC board. So there's 16 channels here, 16 single-ended differential to single-ended converters here, the whole thing duplicated on this side, and then there's these op-amps are OPA 404KP, which are 6.4 megahertz FET input op-amps. There's these Kodak resistor networks. These appear to be based on the data sheet 2K 0.1% 10 ppm per degree C modules. These are SD5001 quad DMOS switches, so those probably provide the multiplexing to select between the different channels. I believe what this does is reads an entire frame off imager A and then an entire frame off imager B, so the speed is halved. And other than that, there's just some 74 HC series logic and some more, a few more of those DMOS switches. And you can quite clearly see the analog outputs all fanning down into this connector, which then goes through the back plane and comes up on the ADC board on over here, and all the analog channels go up to the ADCs. It's also interesting to note the PCB revision J, which implies they've spun this board 10 times. And from what we've seen so far, 3 boards, there hasn't been a single bodge wire, so it looks like they've rather than do bodges on the system, they've decided to spin the boards as many times as they need, which is really nice. This is the IID board. This probably means Imager Interface Digital. This is basically just a giant sea of 7400 series logic that controls the 2 imagers. These are the connections that run off to the imagers. On this of note, we have a couple of 8K by 8 SRAMs, those 8464A, and a few 8-bit DACs here, 3 of them. Other than that, it's all just 7400 series logic. LM337 there is another PLD, and a few delay lines. This board would generate various timing and control signals to control the operation of the two imagers. One thing to note here is the revision on this board. Revision AE, which depending on the numbering sequence or lettering sequence they use, implies at least 25 revisions. And I would love to work on a development team that had the resources to make that many revisions on something like this. I mean, so far we haven't seen any bodge wires at all in this whole thing. This board is the EM DTC Plus. This one is again a C of 7400 series logic and quite a few small PLDs or GALs. This one's only revision B, nowhere near like the last one, which was AE. This one has a 24.576 megahertz clock on it. That just happens to be 8 times the imager pixel clock of 3.072 megahertz. So I'm guessing DTC may mean digital timing controller or something like that. And this clock here is probably the source of the Serializer's high-speed clock, the ones we saw on the ADC board. The video bus interface appears to be responsible for reading data out of RAM and formatting it for display. This connection on the top connects over to the RAM controller. There's a lot of 7400 series logic plus some more lattice PLDs. There's an Altera EP910 PC, that's a 24 macro cell ePLD, and another Xilinx FPGA. It's an interesting mix of manufacturers, Lattice, Altera, and Xilinx on this. The data coming from the RAM controller appears to be differential ECL, just like the data from the ADC board to the RAM controller. Appears there's about 16 channels. These are quad MC 10125 quad differential ECL to TTL converters. And there's some octal flip-flops, and the traces all run over to these Toshiba memories, TC5588P. These are 8K by 8 SRAMs. These RAMs appear to be wired up as groups. Each two are bused in parallel. So we have a 32-bit, actually 33-bit wide bus, because these two here are 9-bit memories. So we have a total of just over 64K of memory. That's more than enough to store one frame. The 240 by 192 frames are about 46K, so this obviously acts as a frame buffer. Likely what they're doing is reading the data out of RAM at full speed, full RAM speed, which is probably similar to the rate that comes off the imager at, and then this buffers the data and it's read out slowly during the when the frame being sent out, the NTC video is being drawn. And there's more logic that probably takes the video, reading it. The FPGA probably controls how the data is read out of the RAM and sent over to the DAC on the video board. They're probably using the one extra bit on these last two RAMs to store some sort of like a frame valid signal or some other video control signal or something like that. One thing a bit odd is they have these parts here, like U48, U43, U57, that are there but don't appear to be tracked into anything on either side of the board. There's absolutely nothing connected to them. And I don't think this is a 6-layer board. I think it's 4-layer. At least all the other chips have at least some traces going to them visible on the top layer. So I'm wondering if these are just like placeholders or just to hold the space and they just left them there. This is the graphics assembly. This is responsible for taking the pixel data coming out of the frame buffer in the card we saw previously, and along with generating the on-screen displays and generating the analog NTSC video out. This has a TRW 1016B7 video DAC. It's a 20 megahertz 8-bit video DAC. There's a weird chip made by Plessey starting in MOH. I can't find any info on. There's lots of 7400 logic just like everywhere else. Lots of gals. There's a few AMD AM9128 2K by 8 SRAM. That's probably operating as character RAM or character RAM to store text to be displayed. There is an MC6845 video timing controller and address generator. This basically, you can program it for different video display formats, like how many lines of text and how high the characters are, for example. And it will generate all the addressing to read the character position and the character bitmaps out of RAM at the correct time. And that's the data from that is sent off to the video DAC. And also, somewhere at some point in the circuit, the video read off the camera is mixed in. And at the bottom here we have some sort of video ZNA 134 video timing controller. Yeah, I can't find much on this part. This is also made by Plessey. It appears to do stuff with video, generating video timings and generating the fields for interlacing and things like that. There's a lot of traces coming off of this connector here, and the other board we looked at previously goes in here, and that has a lot of connectors as well, so the video data must go down there across the back plane. And if we look down here, there's a bunch of traces between those two boards. This MC6845 part is also known as the 6845 CRTC, or cathode ray tube controller, and it was quite common in computers of the era, used for generating the text video displays. And this is another board that's gone through a lot of revisions. This board is labeled the frame buffer assembly. This contains a bunch of control logic, as well as 32 1-bit by 256K DRAM. So this is 1 megabyte of RAM right there. I'm not sure if this is, this may be a leftover from the old version of the system which recorded data on tape, because they would have needed some extra image buffering to save data coming off the tape during playback, for example. This seems to connect mainly down to this connector, which goes over to the next board, which has the main CPU. So I'm wondering if they've just left this in and are using it as memory for the CPU. Have to take a look at that. What else do we have? Yeah, just mostly 7400 series stuff. There's a 25 megahertz crystal up there, or clock. Now this looks like the main control board. This is the SCU assembly. I'm guessing that means System Control Unit or something like that. There's a nice big 68,000 CPU in a DIP package. Two 16K EPROMs for the program. What else do we have? Delay line, we have a non-volatile SRAM. I wonder if the battery is still good in that. This is 20 years old now. This here seems to be clocked at 14.7456 megahertz. Over on this side there's more of the same RAM we saw on the last board. This is again 256K by 1, so there's 512 kbytes RAM there. Other than that, it's not much. It's just a 68,000 CPU that must run the whole system. I just noticed something missing from this board. Can you guess what it is? One thing you don't notice are many bypass capacitors, so I figured they must have put them on the back as surface mounts, but no, there's nothing there. And then I looked under some of the ICs and noticed these blue things. This is really interesting. I've never seen this before. It appears they're using these flat capacitors under the ICs for bypassing, and a little lead. They put two leads through the power holes. You can see, you should be able to see here, some of on the edges, the leads are a bit longer. That's where they have the dual leads coming through. I've never seen bypass capacitors like this, and it's an ingenious way to get more space on a board if you don't have room for bypass caps. It probably produces much better bypassing than having a cap out of the side and running traces in anyway. The communications interface provides GPIB and RS-232 interfaces. That's the GPIB there, and RS-232 on one of these. This has a whole nother 68,000 on it with its own program memory and data memory. I think these each are 32K by 8 SRAMs. This part is a UART. This is a general purpose I/O controller for like general I/O ports. This is a GPIB controller. That's a programmable timer. That's a GPIB bus driver. This must be the GPIB. This is the serial ports. Other than that, just the regular 7400 series logic as used everywhere else. This board is labeled SCU memory. This has several GPIO type functions. It's one of those GPIO controllers. There's two UARTs, one programmable timer, and a real-time clock. And there's a little watch crystal right there for it. When I was looking at this system, when the remote control was the keypad was missing, I was looking into reverse engineering the keypad communications. I found the keypad stuff went to this, and I think it was this UART along with some circuitry over here. One thing I find strange, this has some memory on it, EEPROM for program or something, but there's no CPU anywhere. This must be controlled by the main CPU. Let's see how that battery is doing. Incredibly, that 20-year-old battery is still working. Those last few boards weren't that interesting, just a bunch of stuff you'd typically find in computers of the era. And now we're getting back into the custom, interesting stuff. We have the memory controller board and 3 boards that are absolutely packed with SIM modules, memory. Here's the memory controller. This takes data from the ADC board on this connector, formats it correctly, and then puts it onto this output bus, which connects over to the RAM card. Also has some circuitry to read out data from the RAM and send it to the display over this connector. Mostly 7400 series logic. There's some IDT 7201 512 byte by 8-bit FIFOs, or was it 9-bit? And there's some transparent latches and registers. And these are the ECL to TTL converters. I think those are the TTL to ECL converters for sending data over the cables. A few more PLDs. There's a delay line. Strangely, there's a 78HC11 microcontroller on this. Probably controls how the acquisition is done, or perhaps generates addresses and controls what addresses the images are written to in RAM. I'll take a little bit more in-depth look later into how this formats the data going onto the RAM, because the clock frequency of the incoming data is 24 point some megahertz, which is around 40 nanosecond period, and the RAM is 70 nanosecond RAM. So it's interesting how they slow the data down and widen it out, or widen the data bus, because this is 16 bits coming in and 48-bit bus to the RAM. And finally, here's the memory card. There's 3 of these. These have 18 SIP or SIM memory sticks. These are 4 megabytes each for about 216 megabytes total in the system. That gives about 5 seconds record time. You can see the 3 separate 16-bit buses coming in here, 48-bit total, and they're banked together as 3 groups of 6. There's a bunch of other various control logic, 7400 series as always, more lattice gals, and some CD 7400 series logic. This RAM was not cheap. When the system was made, all the RAM in the system is worth about $6,000 total, if you base it on retail prices at the time. Looks like they had room for sockets, but they just got these modules that you can solder straight in rather than using the having connectors. Seems to make sense. I don't think you'd ever upgrade RAM in this. I don't know if you even could. I've drawn out a block diagram here of the basic image acquisition data path. The data coming in from the image sensor, the analog channels, goes into an ADC. ADC is clocked at 3.072 megahertz. That's provided by a clock divider from the 24.576 megahertz clock. The data goes into a 74166 parallel serial shift register that converts the 8-bit data to a serial data stream clocked at this clock rate. That's then converted to emitter coupled logic. A MUX can select between the video data and data from that the card that generates the video to be burned into the data saved to RAM. That's then converted to differential ECL, and then the data is sent over the cable to the from the ADC card to the memory controller. On the memory, well, this side I've only drawn one of the 16 channels, so there's 15 other channels that join in, so we get a 16-bit data bus. That data bus transmits, on each clock, it transmits all 16 MSBs from all the 16 ADCs, then all 16 second to most significant bits, and so on, all the way down to the LSB, and then repeats for the next data. The memory controller, anyway, the memory controller receives that differential signal, converts it back to TTL through a register, and then onto a sort of I used to call it the high-speed or HS data bus. This runs at the serializer clock rate of 24.576 megahertz. The RAM in this system is, I believe, is 100 nanosecond DRAM, which means the data has to be kept valid on the RAM pins for 100 nanoseconds. And since this 24.576 megahertz clock is about 40 nanoseconds, you can't directly send that data onto the RAM. So what they do is quite interesting. They have a series of registers that can basically sample and hold the data on this bus over 3 separate different memory buses, and those are interleaved so that there's each bus has 120 nanoseconds of data valid time. I've drawn out how that works here. This is each clock of the 24.576 megahertz clock, so that'll be all the MSBs from the ADCs, second MSBs, and so on. That data will be, so there's clock 0 that clocks the memory bus 0, clock 1 clocks memory bus 1, clock 2 memory bus 2. The clock 1 goes high for 1 pulse in every 3 of the acquisition clocks, and that the register for memory bus 0 gets data 0. And since the clock only occurs once every 3, clock pulse occurs only once every 3 of the main clocks, that data remains valid for that entire time, around 120 nanoseconds. But since we have more data continuously coming in, that data is taken by the other memory buses in this interleaved fashion that allows the high data rate that the camera requires. And controlling this is quite complicated because there's all sorts of control signals for all of these registers that have to be controlled at just the right time for all of this to work. This is quite ingenious and a pretty complicated way of doing it. There's also FIFOs in here that buffer the data while the memory is refreshing. So while it's refreshing, it can't receive new data. So these FIFOs take in that data from the camera during that time, because you can't, the data coming off the camera has to be saved in some way. If you stop taking it, it'll be lost. So those, during refresh, those can fill up with data, and then when the refresh is finished, they can be dumped out. And during the horizontal and vertical blanking times of the camera, when it's not sending any data, those can then be fully emptied into the RAM. All of the parts driving this internal HS bus are tri-statable, so you can either have it driven by the image sensor or by the transparent latches that can read data off of RAM. And for readouts, these can select the proper data coming in alternately, sort of just basically backwards, the opposite way that it is written into RAM, and then that's read by the used to display live video or to play back video out of RAM. This power conditioner card doesn't have too much on it, just a bunch of power transistors. I believe these are just operating as power regulators or filters. Yes, the power conditioner card. There's 2 connections that go off to the 2 imagers. And here's all the boards out of the system. Look at that. I don't think I'll bother taking this apart any further. There's not going to be much interesting underneath. It's just a switching power supply. And the boards on the front are just connect all the front panel inputs to ribbon cables. This definitely does take a lot of current at 5 volts. Two big 12 gauge wires, it looks like. The power input on this is around 200 watts. That would put it something around maybe 30 amps at 5 volts, considering inefficiencies and the other voltage rails. I see, I think plus and minus 12, plus 24, and minus 5.2 for the ECL. Now that the teardown on this is pretty much complete, I figure we may as well just compare this with the newer Ektapro high-spec processor. They basically have just taken this version and compacted it down. They've moved the power supply from underneath to the side. This power conditioner board here has been moved to the back, and they just rearranged the front panel a bit. There's no more plastic, this one's all metal. This one, they've also, pretty much all the boards in the card cage are the same, except they've changed the RAM to use 32 megabyte sticks of EDO instead of the 4 megabyte SIMs that this uses. These are, this has 216 megabytes total, this has 864 megabytes, which gives it about 20 seconds of record time. The memory controller on this one appears to be identical. I don't notice any real differences. The same architecture as the other one. Obviously the memory cards have been completely changed. They're using, it looks like a more advanced process. They're using surface mount stuff for the first time we've seen any of these systems. Looks like they've implemented all the logic in a bunch of PLDs, using some these are the bus drivers for the for driving the large memory buses. I'm thinking this is at least 6 layer because I don't see enough traces going to the memory connection here on this layer, so they must be going on internal layers. Now that we've got the processor out of the way, let's take a look at the imager. Okay, we got 4 cards in this with BL's through hole again. There's this piece, what is this, labeled the viewfinder. This does have some at least one surface mount part on it. This has these rubber membrane buttons. Let's see. Looks like this connection here is for the high and low gain switch. That's probably unique to this one. The regular normal imagers don't have this. This one has the switchable gain. How does this come out? Do they just pull out? Doesn't feel like it, no. Probably the whole thing will slide out. Just see if we can get this off. Okay. There we go. That's the back of the image sensor board. Let's just take a look. There's the front of the image sensor. There we go. Something is hitting. What is it? Aha, I found the problem. If you look just under that little white plastic thing in the center, someone has driven the tripod screw too far in and bent the casing up. So that's what's stopping the board from coming out. There's 4 cards in the card cage. Digital high-speed, digital low-speed, and 2 analog sampler cards. The analog samplers have quite a bit of stuff on them. There's 4 of these apparently custom parts. I can't find any information on them. MOH3565. They appear to perform some sort of amplification on the data, analog data from the image sensor coming in here. There's some transistors, a bunch of pots, some quad bilateral switches, and a bunch of 8 megahertz op amps. And then I'm guessing these are some sort of differential drivers to generate the differential signals. These might be termination or resistors for the bus termination for the long, because these would directly drive the long cable. These are very, very densely packed boards. There's almost no free space on these at all. High-speed digital boards just have a whole bunch of 7400 series logic and a bunch of adjustable data delay lines. The low-speed digital is again just some 7400 series logic, some pots for something, perhaps delay time controls. You can see all the analog traces coming off this to go onto the main giant circular connector. Probably won't bother pulling this apart because I don't want to mess up the back focus. That's the distance between the image sensor and the lens mount, but I don't think there's going to be too much interesting on this board. It just looks like a few ICs. And the same thing on this is pretty much just a keypad, and there's some outputs like for a monitor, things for a viewfinder. Not too much on this. No, it's a bodge wire. We've been through the entire system and we have not seen a bodge wire until now. This is, how many revisions has this been through? Revision AH, so even all those revisions, they still needed a bodge wire. And it looks like whatever glue they've used has degraded the insulation around where they use it because the diameter is reduced. I hope you found this teardown of the Ektapro EM camera system interesting. This is an absolute marvel of engineering from the early 1990s. It was absolutely cutting edge at the time. Anyway, hope you found this video interesting. Thanks for watching.